Auzu billahi minash shaitani rajim. Bismillahir Rahmanir Rahim. In tutorial 9.2 related to the concept of modulation, we will solve a question which involves using the Friis transmission equation to calculate the maximum communication distance of two scenarios without the modulation and with the modulation of the baseband signal. Here is the detailed breakdown of the question, component and approaches discussed in given slides. As discussed earlier, consider two scenarios without modulation where a baseband signal of frequency 3 kHz is transmitted directly. And with modulation, the baseband signal is modulated using a carrier frequency of 100 MHz. Now we assume the following parameters for both modulation and demodulation, for the modulation and with the modulation and without modulation. Transmitted power by is 10 watt, and we assume the antenna gain of both the transmitter and receiver is approximately 1. In other words, we assume that both the transmitter and receiver are isotropic in nature. Similarly, the noise signal to noise channel ratio is assumed that 10 decibels and effective bandwidth 3 kilohertz for both cases. And noise power density is 10 power minus 12 watts per hertz. Now we have to compute the maximum distance for both scenario using the Friis transmission equation. We see the transmission equation, Friis transmission equation. We see that power, received power, PR, is equal to PT, GT, GR, lambda square divided by 4 pi capital R square. Where, as discussed earlier, PT is the transmitted power, GT is the gain of the transmitter, and GR is the gain of the receiver. And lambda square, which is wavelength of the corresponding frequency of a modulated signal received by the receiver, and 4 pi capital R square, where capital R is the distance between transmitter and receiver. Here, as we know that lambda is given, lambda we are given is used in the equation, and lambda is equal to C over F, and frequency is given. So we can firstly calculate the lambda, and, and we are required the SNR to define the signal to noise ratio as a PR divided by N, because PR is not given, but with the help of signal to noise ratio and N, we will calculate the PR and received power. And N is equal to N naught dot B. B is the bandwidth of the modulated signal. In the first step, we will calculate for the 3 kilohertz lambda wavelength. Lambda is equal to C over F, where C is equal to 3 into 10 power 8, and frequency is 3000 because 3 kilohertz. So total lambda is equal to 10 power 5 meters. Now, in Friis equation, we have to require PR, but PR calculated with the signal to noise ratio equation, signal to noise ratio dot n, and n is calculated with n naught dot multiplied by b, where b is the bandwidth. So n naught is given 10 power minus 12 watt per hertz, and bandwidth is 3000. So our n is equal to 3 into 10 power minus 9 watt. So the required received power can be calculated when we multiply it by SNR with the n. So n we have calculated SNR is 10 power 1, and N is it in 10 power 3 to 10 power minus 3. So our received power is equal to 3 into 10 power minus 8 watt. Now we incorporated all values into Friis equation, where received power 3 to 10 power minus 8, and 10 multiplied by 1 multiplied by 1 multiplied by lambda square 10 power 5 square, where these are the basically gain of the receiver and transmitter, and 4 pi capital R square. All values are known. So, and GT is the transmitted power, 10 watt. So, R is calculated, which is equal to the 4.6 kilometer. So, we see that if there is no modulation, we directly transfer the data of 3 kilohertz, then our maximum possible distance between transmitter and receiver is 4.6 kilometer for successful transmission. Now we repeat the same steps, but frequency is a 100 megahertz carrier frequency, which is very also for the modulated frequency for amplitude modulation or other modulation. So that's why we calculate in a similar way. Lambda is equal to C over Fc, and C is 3 into 10 power 8. But here F is equal to 100 megahertz. So our lambda wavelength is equal to 3 meters. And because our received power is same, it is independent of the wavelength according to the given question data. So it is 3 into 10 power minus 8, and 10 watt is the transmitted power, 1 is GT, and lambda is equal to 3 square divided by 4 pi r square. And now we calculate the R, capital R, the distance between transmitter and receiver, which is equal to the 159 kilometers. As in previous slide, we see 4.6 kilometers, and now it is 1.159 kilometers. So huge difference will take place when we modulated the signal from 5 kilohertz to the 100 megahertz. This is another serious advantage of the modulation, which is the heart of the modern communication system.